This year, we celebrate 28 years of Java innovation, and Java continues to be vibrant in the Java ecosystem, touching every vertical and every company, no matter size, large or small. And that's because the technology of Java is pervasive through the innovation pipeline of features that we continue to deliver regularly. And that's all encompassed in the current latest Java 20 release. Now, how do we do that? We do that because we stayed true to our principles that have been established for over 28 years, ensuring that we have the trust of the community, trust in that we will do what we say and deliver what we've promised, innovation, and that we will continue to incrementally deliver new features that meet the world's demands of application development in terms of the challenges as well as the opportunities. And of course, the predictability. Predictability that we will release Java as we've promised to do every 6 months, both in March and in September, to bring that innovation to you in a much more rapid fashion. And this is all encompassed by our predictable 6-month release cadence. Gone are the days of releasing Java every 2 years, every 3 years, perhaps every 4 years. We now release Java every 6 months incrementally, bringing the innovation of the platform and the language to you in smaller chunks and in smaller bites. But each release is filled with thousands of performance, stability, and security enhancements, just as it always has. And all of this innovation happens at our Open JDK project, where all of that innovation is done openly and transparently, allowing you as developers to watch, listen, learn, and participate in shaping the future of Java. We do this by investing in long-term projects that try to meet the needs of both the challenges and opportunities faced in modern application development. Things like simplifying the language syntax in Project Amber, thus making Java more readable, writable, and maintainable. Or addressing the virtual threads that are most common in applications for the cloud and microservices. Or optimizing data for machine learning coming from the innovation happening in Project Valhalla. We look forward to your participation in the Open JDK project so you can partner with us to shape the future of Java. We'd also like to thank all of the organizations that continue to partner with Oracle to shape that future. It's incumbent upon Oracle to continue to be the leaders of Java and take on the responsibility of shaping that future. But we would also like to say thank you for all of the companies, as well as all of the individuals who participate in every release to ensure that it meets the quality needs for every application out there. Now, as Oracle invests its leadership in shaping the future of Java technology in terms of the language and the platform, it's also important that Oracle also co-invests in stewarding Java forward, as well as being the leader in that stewardship. The foundation of Java has always been its community, and we again try to invest both in gaining the trust of developers, in ensuring that we are delivering the programs necessary and all of the modalities in terms of learning Java, sharing with Java, and participating in Java. Innovation such that we are delivering new programs, again, that meet the needs, both in short form and long form, and being predictable in that we will show up in the community to partner with you as developers. Two important resources are both dev.java and inside.java. Dev.java is our new portal that encompasses all the information that makes Java so vibrant, from best practices and tutorials and learning information, as well as information on the community, how you can participate and find other peers of like minds, so you can connect, communicate, and collaborate with them. Inside.java is our way to aggregate all of the publications from our developers on the Java team as they provide updates in one location. Now, this wouldn't be possible without the strong Java developer relations team that continue to invest both in programs, content, and the community. You can find all of us socially. We welcome your connection and reach out to us. Reach out to us for questions, reach out to us with suggestions, reach out to us to connect. And now I'd like to hand it over to my colleague, Aurelio Garcia-Ribeyro.
Thank you, Sharat. In this session, I'll give you a brief overview of the features that have been added to the Java platform with the release of JDK 20. Let's dive right in. As Sharat mentioned, JDK 20 is the first release of 2023 and the last release prior to the next long-term support version. JDK 20 replaces JDK 19 and will be superseded by JDK 21 later this year in September. JDK 20 is offered under the no-fee terms and conditions, so everyone can use it in production at no cost. JDK 20 delivers 7 JEPs, all of which are either Incubator JEPs or Preview JEPs. Most library improvements start as incubators. Once they are mature enough, they might be added to the standard in a later release, or they might be progressed from Incubator into Preview mode. Preview mode is a step closer to being added to the standard. Features in Preview are fully specified and implemented, but are impermanent, so they might change in the next release. Previews are the usual way to test language features and JVM improvements, so since those cannot be easily constrained into an Incubator module. Using preview features requires acceptance that the code that you will be writing will likely need to be changed before it can run in a future version. We expect the changes to be small, but there are no guarantees. Now, to ensure that developers know that they are relying on a preview feature, it is necessary to pass along a flag to the compiler at compile time. And it's also necessary, to avoid surprises if you're using a library built by somebody else, to pass a flag at runtime. Preview and Incubator features are only possible thanks to the 6-month release cadence. At all times, the next release is at most 6 months away, so we can afford to ask for feedback before committing to a feature without delaying it for too long. It also means that we are very close to be done, so there is very little time to provide feedback. We ask you to take this opportunity to provide feedback on these features before they get added into the standard. Now, we've grouped the features in JDK 20 into 3 categories. We have 2 language features from Project Amber, 2 library improvements from Project Panama, and 3 improvements from Project Loom, which aims to update the Java concurrency model. We always like to start with language features since they are the changes that are most likely to impact most developers. JDK 20 brings a second preview of record patterns, which makes it much easier to deconstruct records and operate on their components. Record patterns can be nested to access the data at any level of a record hierarchy. Let's take a look at an example. Well, before we go to the example, let's review the 2 changes that got us here. JDK 16 introduced pattern matching to the instanceof operator. Prior to this change, if I wanted to do something with an object, the only way to check if it was certain was to manually test to see if the object was of a type that I cared for. Then I had to declare a variable of that type, manually cast the object into the variable before I could start using it. With pattern matching for instanceof, we gain the ability to do the testing, the declaration, and the casting in a single line. JDK 16 also brought us records, which simplified the creation of classes that were used as simple carriers of immutable data. Records are more than just a way to type a little less code when declaring a class. Knowing that a class is a record will allow us to do some interesting optimizations on it. And it made it possible to even add them into a larger language change, as we will see now. In JDK 20, we can see the combination of pattern matching and record classes. In this example, we have defined a record class called point, with the expected components x and y. In the print_sump method listed here, we want to first test if the object we receive is a point, and if so, we want to use the values of that point. Notice that the intermediate variable p, which is used only to invoke the accessors x and y. It would be better if the pattern could not only test whether a value is an instance of point, but could also extract the x and y components from the value directly. In other words, in this new code, point int x int y is a record pattern. The true power of pattern matching is that it scales elegantly to match more complicated object graphs. For example, consider the following declaration. Let's make the point more complicated. We introduce a color, then we define the color point as a point and a color, and finally we define a rectangle as defined by two color points. We know we can extract the components of an object with a record pattern. We want to extract the color from the upper left point. We could write something like this. Note that the names of the pattern variables do not have to be the same as the names of the record components. But the color point for the upper left is also a record, so we can decompose it even further with nested record patterns. Using nested patterns, we can decompose the outer and inner records at the same time. A record pattern can use var to match against a record component without stating the type of the component. The second preview for this feature adds support for record patterns to appear in the header of an enhanced for statement. That is, if I want to iterate over a group of records and need to operate on one or more of the components, I don't need to use an intermediate variable to access those components. I can get them directly. JDK 20 also brings us pattern matching on switch expressions and statements. Using this feature, we can test expressions against a number of different patterns. In the past, switch statements used to work only on a few types: numeric, enum, and strings. With switch expressions in JDK 14, we introduced other case labels, but you still couldn't use a switch statement to test an expression against multiple patterns. The best we could do at the time would be a chain of if-else-if statements. Pattern matching for switch extends the case labels to include patterns and null in addition to constants, so we can make this code much simpler. As a bonus, this code is optimizable by the compiler. Remember that the case statement has to be exhaustive, so in most cases you want to add a default value. Since you can also test for null, we no longer need to handle nulls in the switch variable before the switch as we did before. We can now make null handling part of the switch statement. To maintain backward compatibility, the default label does not match a null selector. After a successful pattern match, we often need to do some further tests, which can lead to some cumbersome code like this. We could improve the readability if the pattern supported a combination of pattern and Boolean expression. So, allowing when clauses in a switch block allows us to write this in a cleaner way. The first case matches strings of length 1, and all other strings are caught by the second one. The when clause can use any pattern variable declared by the pattern in the case label. We have to be careful with the order of the expressions now. If we were to invert the order and have the case string s before the case with s length equals 1, we would introduce an error. The first case would dominate the second one, as it would catch all strings, even the ones with length 1, making the second label unreachable. Doing so would result in a compile time exception. As before, switch statements need to be exhaustive, so you will likely want to have a default value unless you're switching on an enum or a CL class and have statements for all possible values. Now, those were the language features. Let's take a look at the change in the libraries. The Java libraries are one of the reasons why Java has become so popular. They handle most of the hardest jobs, like proper implementation of cryptographic algorithms or multi-threaded sorting of objects in a collection. They also handle some of the common tasks and tedious jobs that most developers would prefer not to have to deal with. JDK 20 brings us one preview and one incubator, both from Project Panama, which aim to make it easier to interoperate between Java programs and non-Java or foreign code. The first step is a second preview of the foreign function and memory API. The goal of this feature is to make it simpler for Java programs to use functions written in languages other than Java, initially in C, and to safely access memory that is not directly under the control of the JVM. We already have the Java native interface to access non-Java code, but it's a cumbersome tool and it requires some code to be maintained in C rather than Java. This replacement should have performance as good as or better than the current alternatives. Historically, Java developers use one of two ways to access foreign memory. There is the supported way, using byte buffer API, and you also have the hacky way, using sun, misc, and save. Byte buffer is limited to 2 GB size regions. This used to be considered such a large number that it wasn't really a constraint. But nowadays, there are some systems that need access to something much larger. Even worse, developers can deallocate memory on demand. Using byte buffer means that memory is deallocated during garbage collection, which is not really under the developer's control. Alternatively, you could resort to sun, misc, and save and internal JDK API, which will give you access to all of the control that you might need. But as the name implies, it is unsafe. You would be using a non-standard API, which is not guaranteed to be available on all Java implementations, and which might change in future or even in an update release. You also won't be able to rely on the platform to help you deallocate memory correctly. If you get it wrong, and it's quite easy to get it wrong, your program might fail in unexpected ways, including not only JVM crashes, but also silent memory corruption. When it's time to access non-Java libraries, we currently have to rely on JNI, which makes it possible but difficult to use a C library from a Java program. Using JNI, you will have to maintain in sync a Java API, C header files derived from the Java API, and C implementations that call the library. This will mean that for JNI code, unlike the rest of your Java code, you will have to use different toolchains for each platforms that you support, and you will need to keep platform-dependent artifacts updated. This is very tedious, especially if the library itself is evolving rapidly. You will also have to deal with the difference between Java and C type systems. Java uses objects, C uses struct. Java objects must be unpacked by native code. To simplify that task, developers will often try to flatten their objects, or worse, will use sun, misc, and save to allocate off-heap memory and pass around addresses, making the code extremely brittle and unsafe. The new foreign function and memory APIs offer classes and interfaces that will allow you to allocate foreign memory, manipulate and access that foreign memory, control the timing of the allocation and deallocation of the memory, and call foreign functions. Let's take a look at an example. Let's say we want to sort some strings by using the radic sort function of a C library. The first thing to do would be to get a handle to find the function and get a handler to it. With linker and symbol lookup, I can do so with just a couple of lines of pure Java. The second step is to put our variables in an off-heap memory space. First, we're going to have to create an on-heap place for the variables. In here, an array of strings. Step 3, make sure that we properly manage off-heap memory. We do this by relying on a try with resources statement to make sure that the memory is properly freed as soon as it is no longer needed, even if there is an error. Step 4, we create an off-heap place for our variables, which we do with memory segment objects. Step 5, we iterate through our variables, copying them from on-heap to off-heap. Step 6 is using the handle we got on step 1 to call our C library's sorting function. Step 7 is copying the memory from off-heap back to on-heap so our Java program can use them. And what is marked here as a step 8 is simply the runtime managing the allocation of the heap memory, since we have reached the end of our try with resources statements. Now, if you have written any JNI code, these should look dramatically simpler to you. And if you haven't written JNI code with any luck and these new APIs, you probably will never have to. The second API improvement is a fifth incubator of the vector API. Vector computations allow systems to execute operations on vectors instead of applying the same operation to several values one at a time. These can result in significant performance improvements. Hotspot supports auto-vectorization, so sometimes it can detect when a scalar operation can be transformed into superword operations and mapped to vector instructions. The set of transformable operations, however, is limited and fragile to changes in the code shape. This API will make it possible to write complex vector algorithms in Java in a way that is far more predictable and robust. Vector APIs use some of the foreign function memory APIs, which are now mature enough to create this dependency. Here's a conceptual model of a vector operation. Instead of needing to repeat operations, we can achieve the same result with a single pass. The goal of the vector API is to create APIs that are clear and concise. That means that the API should be capable of concisely expressing a wide range of vector computations, consisting of sequence of vector operations composed within loops and possibly with control flow. It should be possible to express a computation that is generic with respect to vector size, or the number of lanes per vector, so as to be portable across hardware supporting different vector sizes. It should be platform agnostic. This means that the API should be CPU architecture agnostic, enabling implementations on multiple architectures supporting vector instructions. As is usual in Java APIs, where platform optimization and portability conflict, we will bias towards making the APIs portable. We want to have reliable runtime compilation, and performance means that on a capable x64 and ARCH64 architectures, the Java runtime, specifically the hotspot C2 compiler, should compile vector operations to corresponding efficient and performant vector instructions. Developers should have confidence that the vector operations they express will reliably map closely to relevant vector instructions. Finally, we want to have graceful degradation, because sometimes a vector computation cannot be fully expressed at runtime as a sequence of vector instructions. In such cases, the vector API implementation should degrade gracefully and still function. On platforms without vector support, graceful degradation will yield code competitive with manually unrolled loops, where the unroll factor is the number of lanes in the selected vector. The last three JEPs from JDK 20 come to us from the work on Project Loom. Project Loom began in late 2017, and it aims to make it possible to write Java programs handling input-output bound tasks that are easy to read, understand, and debug, but also able to match the performance that is currently associated to more complicated codes such as that used by reactive frameworks. Before we dig in, let me try to explain why we started looking into a way to have lighter threads. Let's imagine that I have a very simple system with a single core and a task that is CPU intensive. You could use a single thread and use up all of your CPU power. But many modern computers do not have a single core. The norm now is that all but the simplest systems will have multiple cores. In our example, if the system has 8 cores, then a single thread running on one of those cores would keep the other cores idle. If we can figure out a way to split the task, we can do much better. If we have 8 threads, all of them doing CPU intensive tasks, then the 8 threads will bring us to 100% CPU utilization. And we could do the work 8 times faster. Adding more threads, if each thread is using the core all of the time, won't make this go any faster, since we only have 8 cores. This is what a CPU-bound application looks like. But what if the threads were not using the processor all of the time? What if they were using it only half of the time? 8 threads would keep our CPUs at 50% utilization. So what could we do? Well, we could double the number of threads per CPU. Now, since each thread is working half of the time, we will use 16 threads to keep our 8 cores happy. And if the threads were working only 1/4 of the time, we need 4 threads per core. Our 8-core system can now handle 32 threads and keep the CPU busy. And you can see a pattern here. If you had threads working only 1% of the time and waiting for something the other 99% of the time, you could have 800 threads in our 8-core system. Now, systems on which each task is wasting most of the time, with only a small percentage of time actually needing the CPU, are usually I/O-bound applications. And for this type of applications, 1% of the time is not an exaggeration. Given how much faster the CPU is when compared to the network, you could be looking at 1 to 10,000 utilization. So working one moment and then waiting 10,000 moments. Still, it doesn't seem like we have a problem, right? All you need to do, according to our previous slides, is just to keep adding more threads until you reach the point where your CPU is happy. What's the harm in having a few thousand threads? The problem is that the CPU is not our only concern. The current Java concurrency model suggests that you should create a thread for every task, and then Java will create an OS thread for each Java thread. Java will make it possible to use OS threads without having to learn how to handle the thread for each platform, but you still end up using one operating system thread for each Java thread. And operating system threads are relatively expensive. Operating system threads require a couple of kilobytes of metadata, but they also reserve about 1 megabyte off heap regardless of how much or how little memory the thread might actually use. This in practice means that for most platforms, you will run out of memory if you try to create more than a few thousand threads. And even though that is plenty for CPU-bound applications, it will probably be too little for I/O-bound applications. So, if we're limited to the number of operating system threads that we can create, before Loom, we had two options, neither of which was really good. We could continue using Java threads and assigning one thread to each request. This will make the code relatively easy to read and will allow us to use the debugging tools as they were meant to be used. If we decide to get a stack trace, it will make sense. But you will end up wasting resources. You won't be able to use all of your CPU, and your memory will be allocated but mostly unused. Or you can code around the one thread per request restriction and make it so that a single operating system thread can handle multiple requests. This can be done with tools like asynchronous or reactive frameworks. Doing so can lead to much more requests being processed by the same machine, as you will achieve much higher CPU utilization. But this comes at a terrible price. The programming model would be very unintuitive. It is easy to get things wrong. And if you do get things wrong, the tools won't help you as much. A stack trace from a system using a reactive framework would be close to impossible to decipher. JDK 20 brings virtual threads back for a second preview. Virtual threads are lightweight threads that allow Java developers to continue using the familiar one thread per task model so that we can write code that is easy to understand and maintain. From a developer point of view, a virtual thread is very similar to Java threads, but behind the scenes, it is not tied to a single operating system thread. Virtual threads allow us to achieve near optimal hardware utilization without asking us to change the way that we code. When we use virtual threads, all of the tools that we rely on behave as they did when we use the regular threads. For most developers, switching to virtual threads will simply require switching from platform threads to virtual threads. Virtual threads are assigned by the virtual machine to a carrier OS thread only for as long as they need the CPU. When the thread waits, the JVM will pause them, unmount them, and assign the carrier OS thread to some other virtual thread that is ready to get some CPU work done. Later, when the first virtual thread needs the CPU again, the JVM will assign it to whatever OS thread is available. It could be the same one or a different one. The virtual thread and the developer doesn't care. But there are two scenarios in which a virtual thread cannot be unmounted during blocking operations because it is pinned to the carrier. It is when it executes code inside a synchronized block or method, or when it executes a native method or a foreign function. The Java team has taken care of updating most of the code that is within the libraries. In some cases, your own code might still have some of these issues. Now, as part of the work to test Loom, a small group of people from the Helidon team, and by small I mean one person full-time and one person part-time, worked to create a prototype replacement for Netty, which they called Warp. Netty is used to create high-performance protocol servers and clients. To allow for optimal resource utilization, Netty doesn't use the simple paradigm of one Java thread per request, but instead it has its own set of APIs to allow multiple requests to timeshare the same OS thread. Netty is a mature product, actively maintained since 2004. So it has about 19 years worth of hard work and optimization. Using Loom and dumb asynchronous code and a little tuning, the Helidon team was able to get similar or better performance to Netty in just 6 weeks. And, perhaps more importantly, the code for Warp is much easier to read, maintain, and debug. We got a nice quote here from Thomas Longer from Project Helidon on how they never encountered some of the problems that they had expected to run into. Because they are real Java threads and not some other abstraction, existing code and tools that use the thread APIs just works when running on virtual threads. They work with thread local, they give you the same stack trace and thread dumps, and they work with the same debugger and profiling tools. The graph here shows JDK configured with 200 and 800 threads using a task which has 100 milliseconds IO input-output bound service latency. Now, as you would expect, the darker blue line shows that the server handles the load fine until we push requests to about 10x the number of threads, at which point the latency becomes terrible. Since the arrival rate exceeds the service rate, requests start queuing up in the socket layer and eventually they start being rejected. Now, at the point where the server becomes overloaded, we still have plenty of CPU. The next line, this lighter blue one, we can see that we can postpone that time when we request that we could postpone this time by allowing the JVM to create more threads. The problem is, of course, now we're using a lot more memory. Finally, in green at the bottom, you can see that we were able to achieve full CPU utilization without running into memory problems by using Loom. Now, a great deal of the work into Loom has nothing to do with stack swapping magic, but in clearing roadblocks in the JDK to make it all work smoothly. This meant finding all of the places in the JDK where blocking might happen and replace it with logic that, if running on virtual threads, would instead pause the virtual thread and free up the carrier thread. Much of this was undertaken in separate JEPs, where individual JDK components were re-implemented and put into JDK 13, 15, and 18. This had the extra benefit of not only making these mechanisms Loom ready, but also it cleared up a lot of technical debt. In the end, Loom made almost no significant changes to the JDK APIs, except for the new structured concurrency API. Instead, it provides better implementations of existing and familiar abstractions. If you wrote your own code using threads, you might need to find places where your code won't play nice with virtual threads. The new APIs give you the right tools to find those places and update your code. There is a JDK flight recorder event emitted when a thread blocks while pinned. Since we expect code writing with Loom will have many more threads, we also need to improve how data is passed from caller to callee. Developers traditionally use thread local variables to help components share data without resorting to method arguments. Despite looking like an ordinary variable, a thread local variable has multiple incarnations, once per thread. The particular incarnation that is used depends on which thread calls its get or set methods to read or write its value. Unfortunately, thread local variables have numerous design flaws that are impossible to avoid. Every thread local variable is mutable. The thread local API allows this in order to support a general model of communication where data can flow in any direction between components. However, this can lead to a spaghetti-like data flow. A second problem is unbounded lifetime. Once a thread incarnation of a thread local variable is written using the set method, the incarnation is retained for the lifetime of the thread, or until code in the thread calls the remove method. Unfortunately, developers often forget to call the remove, so per thread data is often retained for longer than necessary. Finally, thread local variables have expensive inheritance, especially when using large number of threads, because thread local variables of a parent thread can be inherited by children threads. When a developer chooses to create a child thread that inherits thread local variables, the child thread has to allocate storage for every thread local variable previously written in the parent thread. This can add significant memory footprint. The more common need, a simple one-way transmission of data from one component to others, can be achieved more efficiently now using scoped values. JDK 20 also delivers an API for structured concurrency. The principle is simple. When sequential code splits into concurrent flows, it must join back in the same code unit. If you write code in such a way, then error handling and cancellation can be streamlined, making it easier to read and debug. Just as structured programming codified best practices into the language for sequential code, structured concurrency does the same for concurrent code. Let's take a look at some sample code. The principal class of the structured concurrency API is structured task scope, the first variable in orange here. This class allows developers to structure a task as a family of concurrent subtasks and to coordinate them as a unit. Subtasks are executed in their own threads by forking them individually. That's the scope fork, also called in orange, and then joining them as a unit, and possibly canceling them as a unit. Understanding the lifetime of the thread involved here is easy. Under all conditions, their lifetimes are confined to the body of the try with resource statement. The use of extractor task scope ensures a number of valuable properties. If either find user or fetch order subtasks fail, the other is cancelled if it has not yet been completed. If the thread running handle is interrupted before or during the call to join, both forks are cancelled automatically. You can clearly see the structure of the code. Set up the subtasks, wait for them to either complete or be cancelled, and then decide whether to succeed and process the results of the child tasks, which are already finished, or fail, in which case the subtask has already been cancelled, so there's no cleanup needed to do. If you need to debug this code, a thread dump will clearly display the task hierarchy with the threads running find user and fetch order shown as children of the scope. Structured concurrency codifies the best practices of propagating failure and cancellation into the API so that they cannot be done incorrectly. Because it follows a discipline of waiting for child tasks, some of the most error-prone aspects, such as cancellations and shutdowns, are made dramatically simpler. Now, I hope you learned a few things about the JEPs that are coming with JDK 20. As usual, if you found these explanations useful, all credit belongs to the JEP authors. You can read more about any of them on the OpenJDK page for JDK 20. Each JEP will have cases that I left out, technical discussions about alternatives that were considered and discarded, and what has changed between previews, and a lot more. The JEPs are only the largest unit of change in each JDK release. There are many other changes that didn't rise to the level of requiring a JEP. Even some changes that used to be called out in JEPs, like adding support for new Unicode versions, which is now almost routine. Some of the issues discussed, new deprecations or the disabling of new features. If you are quick to read here, you could find the disabling by default of DTLS 1.0, right? Any of those could affect you. Now, the JDK 20 release note includes 48 other such changes, which I will let you read at your leisure. If you want to learn more about JDK 20, I recommend two blogs from my colleagues and the Java developer relationship team that Sharat presented a few minutes ago. Nikolai Parlog and Thomas Schultz have written some pretty good articles covering the improvements in JDK 20. Now, if you don't want to remember these links, you should use the URL that Sharat gave us a minute ago, insight.java. By now, I'm sure you're wondering, where can I get a hold of this magnificent JDK 20? Well, you can download it directly under the Oracle no-fee terms and conditions from the main JDK download page in oracle.com. All JDK versions offered under this license won't need you to click an accept license to download them, which means that we can make them available for download using scripts. The links on the main JDK download page can be used with curl and wget to automatically download the current versions of JDK 20. When we release update versions like 20.01, which is now the current version of 20, and 20.02, those URLs will get you the current version, whichever it is at the time. So you will not need to change your scripts after every update. There is a box on the JDK download page titled JDK script-friendly URLs that explains how to use them. If you prefer to get Docker images with Oracle Linux 8 with JDK 20, Oracle offers them through our container registry at oracle.com. If you would prefer to build those images yourselves, you can get the Docker files that we use to create them. We host them in GitHub. And you can then create your own custom images. I hope you found this session useful and that you give JDK 20 a try.